In our first circular motion lecture, we talked about the kinematics of uniform circular motion. We talked about the fact that uniform circular motion is a type of uniform accelerated motion, and that means that it has acceleration, and that means that it has a net force. So in this lecture, we're going to be focusing on the dynamics or the force application of circular motion. So there's a lot that doesn't change whatsoever when we look at this. For example, you've got Newton's first and second law, which says that the net force will cause an acceleration that is proportional to the mass of the object. If there is no net force, there will be no acceleration. So since uniform accelerated motion is a type of uniform circular motion is a type of uniform accelerated motion, we have a net force, and therefore we have an acceleration, and that acceleration causes a centripetal motion. So centripetal acceleration, when we look at it, we say the inertia of an object would cause it to move with a constant velocity in a straight line. So that means that for an object not experiencing any force, that object would travel in a straight line with that velocity because of its resistance to change. There's no net force to cause it to change its direction. So that means that any object not experiencing a net force will follow the vector path of its tangential velocity. But we're looking at an object that's traveling like this in a circle. They don't travel in a straight line. They don't follow the tangential path of their velocity. So the direction is being changed constantly toward the center of the circle. So we established that the acceleration of that object points radially toward the center of the circle. Ignore my imperfect drawing. And so we have centripetal acceleration, which we defined the calculation as AC equals V squared over R, where this isn't a necessarily special type of acceleration, it's just an acceleration. It's just that the acceleration is always centripetal or center seeking. And so that means that we can use this calculation to calculate any acceleration for an object traveling with uniform circular motion in a circle. So remember, force equals mass times acceleration. So for uniform circular motion, there is a net force, and that net force we call a centripetal force, and that means that it will equal mass times the centripetal acceleration. And since we know the equation for centripetal acceleration, you just plug that bad boy in, and here we can say that for any object experiencing UCM, the net force will equal mv squared over R, where we use the tangential velocity and the radius of the circular pathway that it's following, and that would equal the net force. This is still F equals ma. So nothing has changed as far as our dynamics go. So how are you going to know when you're dealing with an object that is experiencing uniform circular motion? Well, the first thing that you got to look at is say, what is the object doing? Is it changing directions? If it's changing directions, it's accelerating. Is it accelerating? Is it doing another type of speed up or slow down? If so, then it's experiencing a net force. And is that force toward the center of the circle? Is the only thing happening that the object is changing directions? So to solve a free body diagram for uniform circular motion, we're always going to call toward the center of the circle positive. So that means that, pulling back our nifty little drawing, right? We're not going to establish this direction as positive. We're going to establish toward the center of the circle positive. And so if we're down here, we're still going to call toward the center of the circle positive. All right, and it's just going to be our convention for problem solving. Toward the center of the circle is always going to be positive. So we're going to draw a free body diagram and find the net force equations. If the uniform circular motion is the only thing happening, then our net force will equal our centripetal force equation, mv squared over r. If there's more than just uniform circular motion happening, then this will be one component of the net force. So a couple of things to remember. I'm saying centripetal force and centripetal acceleration like they're brand spanking new things that we're going to have to learn about. But a centripetal force isn't a new magical force that suddenly is the only force that causes things to go in a circle. Things go in a circle as a result of regular forces and combinations of regular forces. For example, the Earth orbits the Sun because of gravity. The Moon orbits the Earth because of gravity, which means that gravity is what causes the centripetal force, or gravity is the centripetal force for the Moon and the Earth. If you swing something around your head, then a rope is causing that circular motion. So the force of tension is the centripetal force. The force of gravity, the force of friction when you're turning your car on a road. These are just regular forces, and these forces can act to cause something to turn in a circle. So if this is a car, and it's turning in a circle, right? It's got a tangential velocity. And if it's turning in a circle, it's experiencing an acceleration toward the circle, which means that it's experiencing net force toward the circle. Well, what makes a car turn? You turn the wheel turns the axle turns the tires push against the road, and it goes in a circle. Tires pushing against road is contact surface with contact surface, so that means that the net force here is caused by the force of friction. Alright, if you've got in a circle, here's our Moon, here's the Earth. Alright, if that Moon didn't experience a net force, it would travel in a straight line, but lucky for us, our Moon is traveling in a total circle, so that means that the net force here is given by gravity. So the net force here is the force of gravity.